So now that we've learned about polyatomic ions, we can now relate those back to our discussion of acids, because what we can do is relate our discussion of acids and how we name acids and relate that to polyatomic ions, because polyatomic ions can match or bind with a hydrogen that is acidic, and we can have an acid that is made up of a hydrogen and a polyatomic acid. However, there is some naming rules that we have to keep in mind, just like all of our other naming rules. So, if a polyatomic ion, that should say ion, has an ending with ATE or 8, so we're looking for ATE, what we're going to do is change that ending to IC, IC. So this is only when it is paired with a hydrogen, okay, and becoming an acid. And we'll see how we can identify those here in a second. So if it has the ending 8, ATE, we're going to change the ending to IC, and then we're going to add acid at the end. So let's look at the example of bromate. So bromate has an ATE ending. We're going to change that ATE to IC. So this is going to become bromic, and then we will add acid to the end. So when bromate becomes an acid, so it's bound to a hydrogen, it becomes bromic acid. Now, how do we write that formula? Well, if we have the name, we can go to the formula, and all we're going to do is pair up the charge of the polyatomic ion with the correct number of hydrogens. But that hydrogen is going to go out in front. Even though it is a positive, it's the cation, we're still going to have that out front, just like when we have ionic compounds. So, we know that H is H+. Bromate has a formula of BrO3-. So we can see that we need one hydrogen for that one bromate ion. Remember, polyatomic ions are going to stay together because they are covalent compounds that participate in ionic bonding. Okay, so that bromate has an overall charge of -1, so it needs 1 + 1 hydrogen to balance out that charge. And that hydrogen is going to go out in front. So it is going to be HBrO3. So that's the formula for bromic acid. Now there's one last caveat to this, and when we talked about acids, we said it was only an acid when it's dissolved in water, or given an AQ notation, where AQ stands for aqueous, which essentially means dissolved in water. There's other solutions we can use instead of water, but in general chemistry, we're just going to be dissolving things in water, so we can think of AQ as dissolved in water. So HBrO3 does not get the notation of acid or the name of acid until it is put into water. So we would have to change the formula to add that AQ at the end. So HBrO3 would become HBrO3 with an AQ at the end. So if you ever see the name acid, that automatically means that it is in solution and your formula needs the AQ at the end. If you see the AQ at the end and you see you have that hydrogen out in front, then you know it's going to be an acid, so when you name it, you need to put acid at the end. So we talked about this a little bit earlier when we were talking about covalent compounds and naming of acids. So we said HCl by itself would be hydrogen chloride, whereas HCl AQ would be hydrochloric acid. So that's the notation that we're looking to see. If we see AQ, we know it's an acid. Okay, it's going to be an acid, so we need to name it like an acid. So if it's a polyatomic, we need to use these naming rules. So this is the naming rule for if it has an 8 at the end, ATE for the ending of the name. There is also a notation for if it has ITE, ITE. So if the polyatomic ion, another typo there, if the polyatomic ion has the ending ITE or ITE, we're going to change that ending when it's an acid to us, O-U-S, O-U-S. So we change from ite to us, and then we add acid at the end. So we have chlorite, and we want to make that an acid. So chlorite, we get rid of the I-T-E ending, and we're going to add O-U-S. So we get chlorus, and then we add acid to the end. Now, we're going to do the same thing when it comes to the formula. So the only thing that really changes when we're doing our different polyatomic acids is what is its ending? Is it ite or ate, and does it change to ic or us? But other than that, the writing of the formula and adding the AQ is the same as it was before. So we know that we're going to add a hydrogen here, and chlorite has the formula ClO2 minus. So again, I only need one hydrogen to balance out my -1 charge of the chlorite. So we get HClO2. And again, we have to go one step further and write that with the AQ notation to show that it's an acid, because it only becomes an acid when it's dissolved in water. So our full formula for chlorous acid would be HClO2AQ. Now you may have some polyatomic ions where they have a 2- charge or a 3- charge, and in those cases you would just add the additional hydrogens to balance out the charges, just like we did with ionic compounds where we had to have enough cations and enough anions to make the overall charge neutral. Okay, our acids have a neutral charge, so we need to keep that in mind. So let's go through a few more examples of naming these polyatomic acids and also writing their formulas. So for this table, I want us to write the name first and the formula second. Now, if it's easier for you to understand to go from formula to name, then you can write it that way as well. Or if it's easier to go from name to formula, that's fine. As long as you're understanding it, that's all I care about. So we have nitrate. We want to remind ourselves that if this is an ate ending, ATE, we're going to change to ic. And if it is ite, we're going to change that ending to us, OUS. Okay, so nitrate is going to become nitric acid. Okay. Nitrite is going to become nitrous acid. Acetate is going to become acetic. It sounds a little bit different, but that's just because of grammar. So we have acetic acid. Okay, so for all of these, I'm just taking off the ate and the ite. So then I would have hypochlorite would get rid of, and ate would get rid of. So hyperchlorite becomes hypochlorous acid, the main component in a lot of skincare items. And then our final one, we have perbromate. Ate becomes ic, so we have perbromic acid. So those are all of our names. We are just changing that ate and that ite ending to either ic or us, O-U-S. Now we want to write the formula. So remember, all of these are going to be H plus something else. So we know we're going to add that hydrogen. That hydrogen is going to tell us that it's an acid. Now we need to think of the formula for that polyatomic acid, or polyatomic ion. So nitrate is usually NO3 minus. Nitrite is usually NO2 minus. Acetate is, we have a few different versions that we can write it. You can write it as like C2H3O2 minus as well. Both are accepted. Hypochlorite is ClO minus, and then perbromate is BrO4 minus. So let's write these out. So for nitrate, I need 1 hydrogen to my 1 ion, so we're going to get HNO3. For nitrite, I need 1 again, so I need HNO2. For these last 3, I want you to take 30 seconds, pause your video, and complete the last 3 formulas. Okay, I'm going to skip acetic acid for right now just because it can have multiple different ways and it can be confusing where that hydrogen goes. So we'll talk about that in a little bit more detail, but let's finish up these last 2. So let's see, hypochlorous acid is going to be HClO, and perbromic acid is going to be HBrO4. Let's look at acetic acid a little bit closer. So, by our rules that we just talked about, the hydrogen is going to go out in front because it's the cation in this ionic compound. So we would technically write this as HCH3COO, without that minus because I no longer have the charge. So that would be a valid formula for acetic acid. There's other ways that you could see acetic acid written. You could see it written as HC2H3O2, or you could see it as CH3COOH. But in all of these examples, we have a hydrogen that is separate from the other hydrogens present. And that's just to show that that hydrogen, that highlighted hydrogen, is the hydrogen that makes this an acid. So when this separates, it's going to be that acidic hydrogen. So that's why we keep it separate from the other hydrogens present. So these hydrogens here, I didn't combine it with those. I kept it separate to show I made it an acid by adding an additional hydrogen. So we do have to keep that notation in that formula to show the difference. Now I do want to just give one more additional example because I realized I didn't add one of these in. And that's if we have a polyatomic ion that has a charge that is greater than 1. So let's take sulfate. So our naming for this becomes, it's essentially the same. We're still going to have the ic ending, but we do have to add a few extra letters just so that it doesn't sound weird. So if we tried to go, it would be sulfic acid, which doesn't really sound right. So for something like this, we actually call it sulfuric acid. And the same thing happens with if we do phosphate, it becomes phosphoric acid. So if we have a polyatomic ion with a 2 minus or 3 minus charge, we add this URIC to the ending, just so that it sounds appropriate for that, and so that we can understand what element is at the center of that polyatomic acid, because sulfic doesn't really tell us exactly that it's sulfur. So we say it's sulfuric acid. Now, when it comes to the formula, we're going to treat it very similarly to an ionic compound. So we have H plus, and sulfate is SO4 2 minus. Now, because there's a 2 minus here, I'm going to need 2 hydrogens to balance out that 2 minus charge. So sulfuric acid has an H2SO4 for its formula. I can do the same thing with phosphoric acid. That came from phosphate. That's H plus, and PO4 3 minus becomes H3PO4. So we're treating it exactly the same way we do our ionic compounds and how we balance out our charges there.